perhaps the other speaker slides. That's what I had. Okay, so before I get started, let me mention that this is a joint work with my PhD student, Diego Araújo, who's just about to finish, and Danielle Yukimura, both are input. So here's my summary. So we're going to be talking about deep neural nets quite a bit today. So I thought that as a first speaker, I'd attempt to be introductory, at least give motivation for the questions we're studying. And of course, the reason why we're all here and all interested in deep neural nets is because they've been very successful in practice. Nevertheless, they're still somewhat mysterious from a theoretical point of view. And one of the mysteries that Song alluded to in his starting screen, right, with that little cartoon, is that unlike what you would expect from classical statistical learning theory, it seems that the more units, the more complex you make the network, the better. So that motivates the problem of looking at limits of networks when the number of neurons diverges. And we'll look at that and we'll see, at least kind of in an impressionistic fashion, because there's a lot of mathematics involved in making this formal, but we're going to see what kind of model we get in the limit. And I'll try to explain to you some of the difficulties involved in dealing with that. Okay, so for the first part, I just want to remind you, probably many or most people, or maybe even everybody in the audience knows what a deep neural net is. Well, basically, we're going to be talking about functions that they take, well, technically they're functions of x. So x is here, and of a vector of parameters. But we'll think of x as the input, and the vector of parameters is something you can adjust to fit the data better. And we're going to be talking about, or for people who know, networks of complete connections. Let me try to describe them to you, right? The description is going to be perhaps a little bit non-standard for people who are used to, the standard textbooks of the area, but it's basically equivalent, at least if we forget about biases. But yeah. So a network is something like this. So you have the input on one side, you have the output on the other side, and you have a bunch of things in the middle. I mean, let me just say that these things, they're called neurons, and there's L layers of them and N, capital N neurons in each layer. So what happens with neurons in layer one? Well, basically, remember you had this vector of parameters. You should think of it as something that's very high dimensional. So here's, or you can say that's that big vector of parameters is a bunch of subvectors stacked together. So from layer 0, from the input to layer 1, what you have is a function, right? What you do for each unit in layer 1, you compute a function of the input and of this parameter. So this parameter is associated with one of the edges in the previous slide, right? One of the guys like this one. And I mean, when I say parameter, I actually mean a vector, right? Parameter is always going to be vectors. So when you go to further layers, the inner layers, this is perhaps a little bit hard to see, but what we're going to assume is that by now we have computed a function for each one of these neurons in layer L, little l minus 1. And moreover, we have these edges connecting layer L minus 1 to one unit in layer L, which is here. And for each one of these edges, you have, again, a vector of parameters. And so the function that you compute at this place here is this function here. Well, we'll write it as an average of nonlinear functions of whatever you had over here. So for instance, here you had a guy like this one. And this guy is also a function. I'm omitting x and theta for the notation, but this is also a function of the input and the parameters. And now you have another function that's like, you take whatever comes in, you compute a function of that and of the parameter at that edge, and then you sum over all edges, or you take an average, because as a normalization, we need to take limits, right? Again, this is not quite the way we usually write down deep neural nets, but this is going to be how I'm going to use it today. In principle, this function here, sigma, can be completely general. We're going to need that it's smooth somehow. So that excludes, ReLU and a few other nonlinearities, but I think that's just technical. And okay, you do that. Let me go back quickly, right? So you've seen what happens here. You compute these functions, and then you compute these compositions or averages of compositions, and you keep doing that at all levels for all neurons until you finally get to the last hidden layer, and you have to go to the output. What happens here? So here you bring everything together. So you have these units in layer L. Remember, these guys are functions of x and theta as well. And you have a parameter for each edge. And in the final layer, you do this thing that we did before. You compute a nonlinear function of the activation of this guy here and of the parameter. You add up overall edges or overall neurons layer L, capital L. And in the end, you take a final nonlinear function, right? So notice when I say nonlinear, I mean, these functions could be really anything. We're going to need that they're smooth, but they could be anything in principle. And so in principle, these networks could have activations, though you have to, I mean, they could have biases, but the normalizations would be kind of funny. But anyway, what we have right now is a function of x and theta. And this function is just a composition, well, it's a composition of compositions of averages of compositions of functions that's described by that graph that I showed you. And we want to understand this function. So just to make sure we all understand, so all these parameters that describe actually vectors, they can be vectors anyway. These functions, sigma L, are smooth. And the final function that you get is a function of, remember, of x and theta. So theta is a single vector that contains all of these guys here, just subvectors. So you have a very high dimensional function, potentially very highly nonlinear. Doesn't need to be convex or anything nice, but you have it there. You want to understand it somehow. And we're going to be discussing a supervised learning setting, which means the following. So we're going to imagine that our goal is to minimize a loss function like this. So sorry, this thing here should be y hat, right? So we have a loss associated with it. This should have an arrow too. So with each choice of parameter vectors, you have a choice that's just how close y hat of x and theta is to y, where x and y are random in distribution p. So that's what you want to minimize. In practice, we never see this expectation. That's sort of an abstraction. What we have is data, and data is over here. We're going to assume it's an IID sample for a distribution p. And our goal, finally, is to find a vector of parameters, right? That should be data dependent. So we're going to choose this theta hat of n, depending on the data we get. And we want to choose it such that the loss is as small as possible. How do we do that, right? So as I said, this function y hat here is very complicated. It could be very highly non-convex. It could be messy. It could be terrible in principle. But we're still going to use a very simple-minded method to try to optimize it. We just take the empirical version, right? So replace the expectation by a sum over data points, or an average over data points. And now, well, there are many things you can do, but basically we want to follow minus the gradient. So we're going to do gradient descent. That's not exactly what we're going to discuss later, but as the first version, we're just going to say, well, I start from some vector theta and 0, and then I iterate something like this. I say new vector is equal to old vector minus something like the gradient of this function L hat n. Right, so you just go in the direction of minus the gradient. That's gradient descent. We're going to be looking actually at stochastic versions of this. But basically, what you do to optimize a neural net is you run this for a very long time and you stop at after a very large number of iterations. And I mean, of course, I'm kind of skipping all the details that go into this. But the point is that, as we know, and again, that's the reason why we're here, right? Such neural nets, in spite of being very complicated, in spite of gradient descent being very simple-minded, they do surprisingly well in practice in all sorts of supervised learning tasks, and also in supervised learning. So I'm not going to be talking about that. Right, but you remember that in my summary, I had like the first thing was that deep neural nets were mysterious. So maybe now you understand the mysteries, and that is how can such a complicated, messy function be actually optimized in a nice way? How can that do well in data somehow? And but perhaps the biggest mystery, at least from the perspective of this talk, is the one that Song mentioned in the introduction, or I mean, he alluded to with the cartoon introduction, which is that it seems that large networks, large deep neural networks, work as well or better than smaller networks. So, okay, from the perspective of this talk, remember that we had this parameter n, which is simply the number of neurons in each layer of our deep neural net. And we want to understand what happens when capital N is large. And if you're at all versed in classical or kind of, I don't know, pre-deep neural net statistical learning theory, maybe the first thing that will come to your mind is that you should have a kind of bias variance trade-off, right? So that's a traditional, well, I mean, in a field that evolves so quickly, it's hard to say what's traditional or not, but that's sort of, you know, the mindset that perhaps people who are, you know, have a background in parametric statistics understand very well, or, you know, background statistics more generally. And okay, what's the bias variance trade-off? Well, on the one hand, the larger the network, the better you can fit the distribution of the data, right? That's just saying, okay, if I have a network with one hidden layers, there are certain functions you can write. If you have a network with more hidden layers, perhaps you can write more complex functions. You can get closer and closer to the ideal function. Okay? On the other hand, you have variance, which means that more complex models, they're somehow more prone to overfitting, which is really mistaking noise in the data for signal, right? Of course, again, I'm being kind of very imprecise here. Ideas to give the intuition. For people who don't know what these topics are, I mean, they should better study. But it's the idea is very intuitive. It's just that on the one hand, you want to fit the model well, so that says take a large network. On the other hand, we know that if you take a model that's too complex, you can easily interpolate the data, you can easily overfit, or at least in principle. And basically, that means that it looks at the data, sees the noise, and thinks that noise has a meaning somehow. Right? So that's the traditional view. But it turns out that that's okay. And then there's this other thing, which is, again, as I said, for practical reasons, people usually use gradient descent or variance thereof to optimize deep neural nets. Well, we're talking about very high dimensional functions. The dimension depends on the parameter n, which we want to take large. So that dimension is going to be huge, really. And if you go to high dimension, it's not very hard to conceive of functions that are like this, except, of course, this is 2D, right? But these are functions that have lots of peaks and valleys, and you try to minimize them. And of course, it's very easy to get stuck at local minimum, right? So here you have a trajectory of something like gradient descent that gets stuck. Well, this one maybe is able to move to a deeper local minimum. But it's not at all clear that you're going to optimize well when you have a function that's this complicated. But it turns out that, and that's been kind of realization that's been coming in bits and pieces for the last few years. So here I have a paper from 2020, but we have lots of previous work on this topic. It turns out that perhaps this vision that, you know, the more complex you make the model, the harder it is to optimize, and the more prone it is to overfitting, or is perhaps this is wrong. I mean, it seems to be wrong. Okay, so this is what the standard view corresponds to. It corresponds to saying that the capacity here, you should think of n, basically. You should think as the size of the network somehow, a measure of the size of the network. The idea is that as you increase the size, you have two kinds of risk, right? So training risk is how well you do in the data. And that reaches here, 0 here, when network gets so complex that it can interpolate the data. And you have test risk, which is really the expectation that we're trying to minimize the loss function. But that should start going up after a while because of variance, right? It goes down because the bias goes down, but it goes up because the variance goes up. This is the standard view. What happens with deep neural networks, or what seems to happen, is that as you increase the size, you see this double descent curve. You see you have this classical regime where things go as I explained, But then you start really interpolating, and you get this overparameterized regime, and suddenly the test risk, the expectation you want to minimize, starts going down. So this is a phenomenon that we'd like to understand in deep neural nets and in many other contexts too. So this paper I mentioned, I forgot to add the year. There's a very nice paper by Song, and I think it's from 2019, the archive, where they look at something that should be, well, that's clearly simpler than deep nets, which is random features, linear regression, and they show a double descent curve just like this. So in some sense, this phenomenon, the double descent, has been hiding in plain sight. It's something that was always there, but we didn't know. And the results I'm going to present today, they don't prove that something like this holds for deep neural nets. So that's an altogether different issue. But what they do show is that somehow you shouldn't be too afraid of the overparameterized regime, because if you start adding more and more neurons, it's not like your network gets completely wild. What happens is that your network, when trained by gradient descent, it somehow becomes simpler than the finite end objects. It converges to something. Okay? All right, so let me move on. As we're going to see, okay, as people have noticed, and I mentioned that in the previous slide, is that somehow what seems to happen, I mean, how do you explain this phenomenon, right? So as I said, the networks get more complicated. How do you expect that they do not behave wildly? Well, that seems to be related to the training that we use. So using this very simple-minded idea of gradient descent somehow seems to be important, or at least a piece of the puzzle in some cases. Because, and maybe, I mean, a kind of caricature, what happens is this. So you're using the simple method, and it could be, of course, that if you vary the parameters of the network very wildly, you're going to move into very high variance regions of parameter space, where you're very sensitive to noise and you overfit in a bad way, and bad things happen. But maybe gradient descent, what it does is it keeps you in a, well, everything here should have scary quotes around it, right? So maybe it keeps you in a simple part of parameter space, or relatively simple, where you don't get to see all of this noise that could kind of throw you in the wrong directions. And again, this is a phenomenon that has been hiding in plain sight. So for instance, this paper here by Lang and Racklin, it shows that you can do kernel learning, which of course was sort of the the state of the art before deep neural nets. Well, in some sense, they had been part of the scene for a long time, but before they became trendy, the kernel methods were the state of the art. But people, they were the training topic in machine learning, and the theoretical literature mostly dealt with regularized kernel methods, meaning you wanna minimize a loss, but you add a small penalty to penalize very complex models. So you want to avoid, by design, complex models. And what Lang and Racklin show is that if you train this kernel method using gradient descent, somehow you don't need to do it. In certain very high dimensional settings, I mean, there are lots of caveats and assumptions, but the basic idea is this, that simply by using gradient descent, you're gonna be learning with kernels in a way that doesn't drive you completely crazy. So you don't need to regularize somehow. Gradient descent is doing that for you implicitly. It's something like, well, it's because you're very high dimensional, you could find lots of minima for the empirical loss function, but you end up finding the minimum with the smallest norm, maybe something like that. Okay, but this is not really my topic. The idea that I want you to get from this slide is that there's a phenomenon to be studied, which is very large networks in this very overparameterized regime. Somehow they should get simpler. And we want to study that from the point of view, not only on the network, which we're trying to optimize, but a network that we're trying to optimize via gradient descent. That's what we want to look at. And now I can finally say, well, I mean, already what a result in the paper is. Again, we don't prove that this double descent curve holds for deep neural nets or even for neural nets that we consider. What we do prove is that if you follow a very large network that's being trained by a stochastic gradient descent, it has in some sense a limit when n goes to infinity. And I mean, I call this, again with scary quotes, I mean, I should have add even more scary quotes here. There's a kind of regularization by law of large numbers. I mean, and what I mean is this. So as we're going to see, averages are, I mean, I already showed you the formula for the networks. They all involve averages of lots of terms. And averages, we know, have a regularizing effect. When we add lots of independent random variables, we get, by the law of large numbers, something that's really constant. If we go to sort of a second order approximation, we get something that's like constant plus a normal with small variance. And basically the details of the constituent random variables that you put in, as long as they have finite variance, they essentially vanish, right? So all that remains is the mean and the variance of the original distribution. And so this is what I'm calling, in very loose language, regularization. I mean, I'm not proving that somehow the networks solve regularized optimization problem. What I am proving, what we are going to see, is that somehow the networks with lots of neurons, they're described not by a very high dimensional object, but by simpler things, well, simpler, at least from the point of view of a mathematician. Okay, so let's see what that is. Again, let me show you the network, right? Again, remember that here you have functions, they're defined in terms of the input and neuronal connections. So this is 0. And then you have these functions that you define in terms of, you know, averages of a linear combination of these guys. And then you have other averages and compositions, and finally you get to the output. And again, I remind you, n is the number of neurons per layer. We're going to assume that these numbers are all equal, though that's not quite necessary. And we're going to be looking at the limit when this number diverges. Everything else remains the same, including the number of layers, that's going to be constant. The dimensions, remember that each parameter, each one of these guys lives in some RT, something like this. And we're going to keep these dimensions fixed, but it's only the number of neurons that's going to diverge. Okay, so let's describe how we initialize a network. And the way we do it in our paper, which is sort of close to what people do in practice, is we assume that the initial settings for all the weights, for all these parameter vectors associated with the edges in my graph, they're all independent random variables at time 0. And each one of these guys follows a distribution that depends only on its level. Or, I mean, so maybe I can go back to the previous slide. So the random variables I put initially on the edges, they're all independent. And if I look at a vertical section like this, they actually have the same law. But the law can change from one section to another. So here I have others, here I have others. These laws can change, but they're all independent. And now the evolution is going to look a little bit funny. And I see I forgot to close curly brackets here. The evolution, for technical reasons, which I'm going to briefly allude to later, I mean, that it's a technical assumption that has been lifted in later work by others, which I'm going to discuss later. So we're going to assume that somehow, let me go back again to the picture, the weights here between the input in layer 1 and the weights between layer L and the output, they remain fixed. So these weights are not going to be learned. So you can say they're random features. I mean, so the first layer of the networks has random features of the input, and somehow you have these random features also close to the output. All other weights, they're going to be learned, they're going to be they're going to evolve by gradient descent. And by that, I mean the following. So you have for each one of the edges, right? So this describes an edge in my network. And this is an edge between layers L and little L plus 1. What I'm going to do is I'm going to change this vector of parameters via the gradient. But you see that's a stochastic gradient because basically at time k, I'm using up the example xk, yk. Remember that xk and yk, k equals 1 to n, are IID data points. And what it claims that even if you condition on the past, if you look at the expectation of this expression over here, this is going to give you minus zeta of t, the gradient of the loss function computed at, well, the gradient with respect to this specific random variable, right? So theta, sorry, this is going to look a little bit messy, of theta. So it's stochastic gradient descent because at each step I'm using a fresh sample, a fresh data point for my distribution that's completely independent from everything else. And in expectation, this follows the gradient of the population loss, right? The gradient of that expected value that we want to minimize. Okay. Right, so let's move on. And here's the main result, at least the first version of it. And suppose you run a gradient descent for k, which is a multiple of n squared steps. Remember that n is a very large number, so this is large. So t is a constant here. And you have this step size, which is going to change in a way that depends only, well, this should be a smooth function. In general, all functions, all the activation function, everything should be smooth. This should be smooth as well. And you take the step size to be epsilon times something that's this alpha of k divided by n squared. So sometimes what this is saying is that the correct time scale to look at things is n squared, right? If you want to see a limit. And I also assumed that there are at least 3 hidden layers, and maybe I'll explain why that is later. And the result, okay, first part of the result is that if you look at layers, I mean, remember, I have input, I have layer 1, and then 2, and then up to capital L minus 1, capital L, and output. And these here, they are static. So first part of the result says that if I look at any guy here in the middle, I can basically, right, up to small error, I can write the state of that parameter vector, that weight of an edge, say somewhere here in the middle. I can write as a deterministic function of my weighted times 0. And that's true for everybody, right? This function is the same for everybody between layer little l plus 1. The only weights that do not quite satisfy this rule are the weights over here between layers 1 and 2 and layers L minus 1 and L. And for those guys, you can write them down as deterministic functions of themselves at time 0 and the value of this edge, right? So this guy connecting two neurons, one layer 1, one layer 2, right? Here and here. And so this would be theta of I1, I2 of layer 1. And what I'm saying is that if you want to know its value, you have to know also the value of this guy. And everything's up to small errors which vanish in expectation or in probability, or say stronger things as well when n goes to infinity. Okay, what does this mean, right? So, well, it means lots of things. So first of all, notice that this, well, I mean, this is sort of expected. Look at these guys first. You can see that given that they were independent at time 0, which we're assuming, they must remain independent at all times, at least up to an approximation error. Why is that? Because I'm saying, well, at time 0, they're independent, and whatever they are at time k, where k is equal to t times n squared, whatever they are at time k is basically a function of what they are at time 0. So if I take independent random variables and take functions of them, of the individual variables, these functions are still independent. So that's for all layers except for the ones that are close to the input here or close to the output. But these layers, they have a dependency just one or the other network. Wait, so let me, we're gonna see that later, but let me just illustrate that by saying, okay, you have layer 1, 2. Remember that these weights here are static. And what I'm saying is that if I look at one of these guys here, it will depend in general on this guy, but not on everything else. And you have similar at the near the output, but with a kind of flipped image. So, okay, this slide is already kind of messy, but this is the first approximation to result. And let's try to do better now, or give more information. Sorry, it's somehow. Oh, okay. Sorry, I need to. Okay, good. Right. So again, this is sort of the dependency picture in a network. So you know, we have edges all over the place. Each one carries a wave vector. And basically the edges are blue, which are everybody except these guys and these guys, right? So yeah, everybody except the guys in here and here, they're independent from one another. The brown guys, I mean, basically what this is saying is that this guy here depends on this edge. And this guy here depends on this edge. So for instance, if I'm missing several connections here, but in the limit, these two weights, they're going to be dependent on one another because they both depend on this guy. So there's a non-trivial dependency structure that arises in the limit. It's not that everybody's independent, as in time 0. It's not like everybody is completely dependent. So it's only certain dependencies that remain when the number of neurons diverges. And one of the consequences of that is that you can write down your loss function. And I mean, this is a kind of intuitive result. I have to make it more precise. But you can write the function computed by the network at time k. Remember, k is t times n squared. You can write it as another function of the point x, the input, and a probability measure, which is a probability measure describing the law of parameters along a path, right? So what am I saying here? I'm saying that if you look at a network, you look at these guys, they are like a path in the network. So it's like you have neurons and sorry, let me erase one here. And this. So I'm looking at the weights along the path. I chose one path here. So from input to I1 to I2, maybe I need some dots here, IL, and then I have the output. I look at the weights along a path. These weights have a certain asymptotic law, which does not depend on which path I took. And the asymptotic law, these weights determines my loss at time t times n squared. Okay, as I said, I'm being very impressionistic here. I'm writing down the formula for these things is very time consuming. What I want to do instead of writing them down, I want to teach you how you can compute them yourself. Okay, right. So let me mention before I continue that there are lots of previous results related to what we proved, right? So my talk and this whole workshop have the words mean field in the title. So the mean field basically is related to the appearance of these measures and the structure they have, and the fact that, you know, lots of independencies arise at the limit. Well, okay, I don't want to make mean field too precise a term because there's no universal agreement on what it actually means. But mean field models of this kind that we're discussing here had appeared before our work in the case of shallow networks, which, as May said, the introduction is It's very different for the case of deep nets, but still all these papers were important inspiration for us. So there's this paper by Song, Andrea Montanari, and Nguyen, and Nas, and these other two papers here as well. They all consider the case where L, the number of hidden layers, is 1. And in that case, you have a lot of structure. Perhaps this paper here, the first one, was the one that said the most about the structure. You can describe this measure mu of t that appears in the limit as a solution of a PDE that can be said to be a convex gradient flow in the space of probability measures with a certain metric that I'm not going to discuss. At least not right now. So, and because this PDE is well studied, I mean, there are guys like Luigi Ambrosio, Gigli. Well, I mean, lots of eminent mathematicians have studied these convex gradient flows in the space of probability measures. These, I mean, there's also, no, there are many others, right, including a few Fields medalists. So by using the theory of these PDEs, they can show that the limiting object evolving in time, and it's evolving towards a limit, right? Which is very important for the particular finite networks. It means that if the number of neurons is large and you run the network for a certain amount of time, you're probably getting close to this limit in time of the infinitely wide deep neural net. Okay, that's for shallow nets. For deep nets, so there had been previous work as well, including by Signano and Spinopoulos, another one of the speakers, by Nguyen and Pham. So the first paper here considers a different kind of limit, where in some sense you're sending the number of neurons to infinity, but layer by layer. And as they note in their paper, I mean, there's some technical difficulties that you have to face if you want to take a limit when all layer sizes go to infinity simultaneously. Perhaps our greatest merit is to have tackled these difficulties in one specific setting. Right, and then more or less around the same time as their paper, a bit before actually, this paper on Nguyen appeared, where he gave kind of a general scheme of what this limit should look like. But kind of, on the one hand, he was very precise. It was a very precise prediction of what the limit should be, involving stochastic kernels and stuff, and it was not completely rigorous. And then there's a later paper for this year by Nguyen and Pham, where they consider a more general model of deep neural nets than we do. So they can consider dependent initializations. If I understand that paper well, it's not yet completely general in some sense, but what they do obtain is that under certain conditions, I mean, there's actually a more recent preprint where they sort of finish that proof somehow. They also obtain a convergence of the infinitely wide neural net, which is also evolving through time and via gradient descent. They obtain that network converges to a limit, which again is very important, and it's not a topic that we discuss at all in the movie. Okay, so let me now try to describe the limit, since I basically told you that there is a limit, but not what the limit looks like. And so the questions we're going to be trying to address for the remainder of the talk is, how do we compute this measure mu of t? How is it relevant to describe the evolution? And there's this question here which is sort of intriguing if you've never seen these mean field models before, but it's a little bit intriguing anyway. How can you have so much independence of the weights in the limit? Because remember, if you look at what gradient descent is doing, it's the gradient of one of the weights of one of these parameter vectors involves all of the other weights, right? So it's not at all clear at first sight that you're going to have a lot of independence of the limit. In principle, it could be that all these weights become finitely dependent, and there's not much you can say about them. Well, it turns out that the fact that you have these independencies in the limit is part of the simplification that you get when it goes to infinity. At least that's one interpretation can give it. And as we're going to see, these two questions are related to the fact that we have a McKean-Vlasov type model in the limit. But perhaps it's easier to understand how you could heuristically guess that you get independencies of the limit from a more heuristic, from a, how you could guess that there are independencies from a heuristic argument. Right? So remember that everything boils down to computing gradients. And I'm writing here the gradient of the loss, right? Not the loss, sorry. The gradient of the function computed by the network in terms of this parameter vector. So this notation perhaps is not very precise, but it doesn't matter. I mean, you can think of this as a partial gradient in this vector of parameters. And it's well known from practice that, deep neural nets are a very complicated composition of functions. However, writing down their derivatives is not that hard. You just have to use the chain rule systematically. And you can write things very nicely in terms of backpropagation. Okay. So, and when you do that, and you write down this derivative here, you get lots of sums and lots of averages in our case, because we're normalizing things. And these averages, they involve paths going forward in the network and paths going backward, right? So here I'm thinking that I have a weight that's in the middle, so it's far from the input and the output. And then when you look, so it's connecting neuron I sub L in layer little l. So neuron I sub L plus 1 in layer little l plus 1. And there are lots of paths going back to the input and lots of paths going forward to the output. And when you get these things with the normalization we're using, you get sort of averages of the paths. We're going to see that they're not quite averages, but they're pretty much averages. And these averages are over things that go forward and back. Okay, and then what happens? Okay, let's just try to see where you get one of these averages, right? So if I'm looking at what happens if you try to compute the derivative of the network in terms of the activation, in terms of that thing ZIL, that's over here. So if you do that, you take the derivative, you see you get an average over things that, okay, these guys here, to compute them, you have to look at, paths from the input to this guy, lots of them and kind of averages. But at the same time, when you compute the derivative, you have this derivative, right? Remember that you have connection from IL to IL plus 1. So when you write this guy, you're also going to be counting things that go forward in the network. And if you iterate that, you're going to be getting paths and averages of averages. And I mean, not quite that, because some of these averages are inside the functions. So it's not quite an average of averages. It's an average of a non-linear function of an average of a non-linear function of an average, or something like that. And so you can do all of this and convince yourself. I mean, if you've never seen this, it's perhaps a bit mysterious, and I'm not going to try to do much about it. But you can sort of see that when you write down the gradients, you get lots of averages over paths or averages of linear functions of averages. And okay, so if the ansatz we use is very simple, so if these averages over many paths become integrals in the limit somehow, then you can write all of these partial gradients as things that are like functions, right? Remember, I'm looking at an edge that's in the middle of the network. So lots of paths going back and forward, right? And when you write it down, if you pretend that all averages are integrals, you get something that's simply a function of the weight itself and of this probability measure that describes the distribution of the weights. Okay, so that's a heuristic. But the point is that when you do this, you see that the evolution of this weight, this guy here, it's not coupled to the other evolutions in the network, right? But it's coupled to the evolution of this probability measure, but not to anything else, because it depends on itself and on the measure. And I mean, kind of the physical intuition is like you have a particle, it's interacting, but not too strongly with many other particles, right? So in the limit, if the number of particles is infinite, what this particle sees is not its interaction with individual particles, but only a kind of integral of the interaction. And therefore, it becomes in the limit decoupled from the other things. I mean, that's sometimes called propagation of chaos. It's not quite the classical concept here, but it's very much related. So this appeared with Mark Katz's paper in the 50s.
Roberto, sorry to interrupt, but you have 3 to 5 more minutes.
Okay, great. Right, so this is the ansatz for, again, edges are far from the input to the output. There's an exception, however, if you have an edge that's too close to the input or the output. So this guy here, it has lots of paths going forward. It has a single path going backwards. And that's a path where kind of you have this weight that we label 1, theta 1, and 0. So it stands to reason that when you replace sums you replace averages by integrals, you're gonna get a drift term that depends on, well, on the particle itself, this guy, depends also on this single guy that lies on its path backwards, and on the measure, describing the things that go forward. Okay? Right, so, and that's where the dependency in the limit appears, right? Because this guy looks at this guy to decide how it's going to evolve. So the main concept of the ansatz, remember we talk about this measure over paths, right? What the distribution of these weights over a path looks like. And the concept of the ansatz, remember that in our assumption we have these random features close to the input and output, so these guys are static. And what happens is that you expect this weight to evolve in a way that depends on this guy, this weight to evolve in a way that depends on this guy, and now the other weights, they have no dependencies with nobody else, right? So first case, this one here, this one here, 2 is like one of these guys. Of course, there's a third guy that I didn't write down, but it would depend on this. So, okay, if you look at the whole vector, I mean the whole vector of these weights here, the vector would be this guy. And if you rescale time appropriately, you get an equation where the evolution of theta of t is given by a drift term. It's an ODE, but an ODE that depends on its current state and depends on the probability measure on the path, right? Because probability measure shows up here and here. It depends, the initial law of theta 0 is mu 0. And then there's this additional self-consistency equation, because remember, this is the vector of weights along the path. Because the initial conditions are random, it's random at time t. And we know that this mu of t is a distribution, the probability distribution of these weights along the path. So theta evolves according to mu of t, but it must be that theta of t has law of mu of t as well. And that's what McKean-Vlasov boils down to. So let me quickly, okay, if you really want to write down the equations, I'm just going to say, write down everything in backprop and replace all sums with integrals, assuming that what's in layer 0, layer 1 are dependent, what's in layer L is independent, and what's in layer capital L minus 1 capital L is dependent. Everything else is independent as described before. But in any case, you're going to get a system like this. And again, as I said, it describes the law of a particle that interacts with so many other particles that actually sees a deterministic cloud or something like that. And sometimes people study that with a diffusion term as well. In our case, we have no diffusion. So there's a history to the subject, and perhaps the best way to summarize the difficulty that we face is that, okay, there's a history that starts in physics, plasma physics. McKean first defined the class of nonlinear Markov processes, he called them. There's lots of existing uniqueness for the results for these processes under standard conditions, but they don't apply to our setting. Because in our setting, we have to look at a discontinuous McKean-Vlasov process. And this is a key difference perhaps with other papers. In those cases, standard results apply. In our cases, they don't. So let me just say how they do not apply. So basically, when you write down the equations for these weights that are close to the output is here, L minus 1. The measure mu shows up here via conditional distribution of this guy given this guy. And there should be a 1 here. And taking conditional distribution is a very discontinuous operation. So he had to develop a theory that deals with the discontinuities we face in our problem. Basically show that discontinuities don't really matter somehow. If we restrict the class of potential solutions, then they don't really matter. But yeah, so let me skip this and just give an overview of what we did. So what we have seen is that the network somehow is simpler in the limit when n goes to infinity than for finite n, and it's a regularization by this averaging process that's really a law of large numbers. Then there are many things missing. I mean, you want to consider more general network architectures. Want to have more general results for convergence in time with the limiting object. Goyen has results about that, but perhaps it can be even further generalized. And there are some directions I find very interesting. One is to consider networks where the input dimensions somehow also go into infinity, which makes sense perhaps for images or signals as subsample at larger rates. And we also, one thing I'd really like to understand is to have some, like for Markov processes or PDEs related to them, we have a general criterion for convergence to a limiting distribution. We have such things for McKean-Vlasov processes. That, as far as I know, is an open problem. So yes, I'm sorry. I'm gonna finish here, and thank you for your attention.
Thank you, Roberto, for your nice iPad talk. Now let's have a few minutes for questions. The audience can just unmute themselves to pose your question. And actually, I have one question. So, Roberto, is there a way to characterize the stationary point of the limiting object? And can you show that this limiting dynamics is minimizing some energy functional or like free energy functional? And
no, that's something we did not manage to do with the tools we had. So you can characterize, I mean, you can write down the PDE and characterize the fixed points, right? And then kind of write down the weak formulation of the PDE and characterize the fixed point. And I mean, so the first thing we tried to do, and we're not successful, was to write it down. I mean, maybe we're lucky and there's still a gradient flow with a convex potential, like in your paper. That doesn't seem to work. Then we tried to write it down as a gradient flow for some energy.
Excuse me, Roberto, I cannot hear you. Roberto, are you here? Did just Roberto lost his connection?